Welcome to the lecture 2.5 on transformations in college algebra. Today's image you see is me as a magician, Chada, because we are looking at how we transform graphs, if you will, how to make them taller or shorter or fatter or thinner or to flip them, okay? I imagine all of us would like some magic to get either taller or stronger or thinner, etc. And so that's the idea of the icon. So welcome to this lecture. And today's brief pause is about taking responsibility. Your attention, please. No one is coming to save you. This life of yours is 100% your responsibility. Um, as we move from like high school to college, um, the shift in responsibility really changes for our learning. Not a lot, but it really is, it should be a huge mental change for yourself in that in K through 12, your instructor is largely responsible for your learning and motivating you, etc. But now in college, that's all on you. Your teacher acts as a guide, but it's your responsibility to make sure you understand the materials, to access the materials, um, to follow the instructions of your professor, etc. And so, just like really in all of life, the majority of the responsibility is on ourselves, and it's certainly here in college. And the difficulty is that the transition doesn't look different. You know, we're in a classroom. Obviously, we're not right now, but we're in a classroom. It looks like high school. It feels like high school. May even smell like the classes I've taken. So it's hard for us to make that mental shift sometimes. But this changes really our level of maturity about taking responsibility for ourselves and really moving from kind of the child mindset to the adult mindset. Accept responsibility for your actions. Be accountable for your results and take ownership of your mistakes. Nothing is more true both in college and life and especially work, um, that taking ownership of mistakes is key. People tend to trust colleagues that they know are forthright, etc. A huge workplace lesson is that when you make a mistake, and everyone makes mistakes, we will all make mistakes, even later in our career, take responsibility for that mistake as soon as possible. If you can, if it's an easy fix, go ahead and fix it first and then take responsibility for it as you move on. When you take responsibility, own it. Um, I didn't show up for the meeting, I didn't have my deliverable, etc. Um, and apologize. And then, if you really want to explain it, and this is where people spend the majority of their time telling a long story about their aunt that was in the hospital and da 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 da, paragraphs long. If you want to explain why the mistake happened, and that's okay, you need to be brief, you need to be high level, and you need to not take more than one or two sentences. If you take a long time, then you're actually not only causing problems for people by the mistake, but now you're taking up more of their time to read about why you made the mistake. It's okay to say, I had some personal situations going on that took my attention away from this, and I apologize. I fixed it, and I commit to do better. And that's the last thing. Make a commitment to change and what you'll do in the future. Accepting complete responsibility for your life means that you refuse to make excuses or blame others for anything in your life that you're not happy about. If you don't like where you are, it's up to you to make changes to get to someplace different. In a lot of rehab programs, they talk about the definition of insanity is doing the same thing but expecting different results. If you don't like what you are, you probably need to change something that you are doing or how you're doing something to get to a different place. And our last quote is by Abraham Lincoln. You cannot escape the responsibility of tomorrow by evading it today. And this is a big one for me because I am a procrastinator. Due dates are important to me, and I tend to wait till those due dates and then make the changes. So being on top of things can really change that. But if I don't take responsibility today, that same stuff's going to be there tomorrow. Okay, let's begin our lecture. Today we're looking at transformations. Given the graph of a function, graph its transformation under translations, reflections. Translations are when the graph moves left or right or up or down. Reflections are when it looks almost like symmetry. It reflects across the x or y axis. Stretchings, this can be making something taller, stretching it vertically, or fatter, stretching it horizontally. And shrinkings, this could be making something shorter vertically or thinner horizontally. So we're going to look at all of those things today, and hopefully this will be pretty clear. But if you need to, go back and review. So vertical translation is the first thing we're going to look at. And this is when you have an outside plus or minus of a constant. So for b greater than 0, the graph of y equals f of x plus b is the graph of y equals f of x shifted up by b units. Very intuitive. You see that we are adding a constant outside of the function, f of x plus b. We're just adding a constant outside the function. So here our green function is the original 3x squared. In kind of purplish blue, you might see 3x squared plus 2. So this is that same shape, that same graph, but shifted upwards by 2 units. Similarly, the graph of y equals f of x minus b is the graph of y equals f of x shifted down by b units. And here in kind of a reddish color, you see y equals 3x squared minus 3. Again, this is the graph of 3x squared shifted down 3 units. Okay? Notice the constant is being added or subtracted outside the primary function. Outside the function. So we're just adding a constant or subtracting a constant. Okay? When we're talking about horizontal translation, we're talking about moving left or right. This is when we have a constant being added or subtracted inside the function. So notice here, for d greater than 0, the graph of f of x minus d. So we're looking at the graph of f of x, and we're subtracting or adding something to the x value. And this is happening inside the function, inside the parentheses. Okay? The graph of y equals f of x minus d is the graph of y equals f of x shifted to the right d units. Now, one of the things that happens here is this is counterintuitive, okay? Notice we're subtracting d, but we're subtracting d, which is 2. We're minusing 2, but we're moving in the positive direction 2 units, 1, 2. Okay, so you have to kind of be mindful of that this is the horizontal translation is counterintuitive. The graph of y equals f of x plus d is the graph of y equals f of x shifted to the left d units. So when we are adding 2 to 3x squared, we're actually going in the negative direction 2 units. Negative 1, negative 2. Okay? Notice a constant is being added or subtracted inside the primary function. It's being added or subtracted to the x value, and it moves in the opposite direction we would expect. Plus d goes in the negative direction, minus a constant goes in the positive direction. And notice these are essentially composite functions. So we had 3x squared. Notice that we added inside the parenthesis, it wasn't 3x plus 2 squared, it was 3 times the quantity of x plus 2. Remember from last chapter, we learned about composite functions, how to put a function in place of x, and then this became a composite function. Okay? Reflections. The graph of y equals negative f of x is the reflection of the graph of y equals f of x across the x-axis. Think of x symmetry where you replace y with negative y. Now, why is that? Because notice for every x value, let's just say I had the top half of the graph here. If I wanted to reflect it below the x-axis, all I would have to do is change the y values to negative, and then I would get the same exact shape, but underneath. Okay, so a reflection across x is very similar to x symmetry. The graph of y equals f of negative x. Notice now we've applied the negative inside the function. We've applied the negative to the x value, is the reflection of the graph of y equals f of x across the y-axis. So again, we can think here in terms of y symmetry, where we replaced x with negative x, and we can see that again here. So if I had the graph to the right of the y-axis, and I wanted to reflect it to the left, I would just change the x values to negative values. Here I have 3, 2, and if I wanted the reflection, I'd have 3, negative 2. So I'm just replacing the x values with negative x values. Now, when you're doing these, you could use your function and get a table of values, and then simply for reflection across x, replace each y value with its negative value in that same table. Similarly, when you're reflecting across y, you would replace in the table, you would replace each x value with its negative or opposite sign. So if a point xy is on the graph of f of xy, then x reflection is on the graph of y equals negative f of x. Again, notice here we're changing the value of the y, the polarity, not the value, excuse me. We're changing the sign of the y for x reflection, and for y reflection, we're changing the sign of x. Y reflection, negative xy, is on the graph of y equals f of negative x. Okay? As an example, reflection of the graph y equals 3x cubed minus 4x squared across the x-axis. Okay? There's our original function in green, and we want to reflect it across the x-axis. So for x reflection, remember we replace y with negative y. So here we are going to multiply both sides of this equation by negative 1, because remember f of x is y. We multiply through and we get f of x equals negative 3x cubed plus 4x squared by simply doing the distribution. And there you can see that new formula for the reflected graph across the x-axis in blue. Okay? So for reflection across the x-axis, we're changing the y's polarity, the sign of y. Replace y with negative y, which means that you would multiply the entire function by a negative 1. And here you can see that the x-axis is our mirror. It's where we're reflecting across. What you see above is the same as what you see below. Another example, for reflection of the graph y equals x cubed minus 2x squared across the y-axis, here we have a green dashed line, and we want to reflect it across y. Well, remember for y reflection, we replace the x with negative x. So everywhere we have an x, we're going to replace it with a negative x. Remember, if anything is happening to that variable, for example, in the second term, we're multiplying it by 2 and we're squaring it. Actually, technically, we're doing that opposite. We're first squaring it because exponents become before multiplication, and then we're multiplying it by negative 2. So in order to do this, to find the new formula for the reflected function, we want to put the negative x in parentheses. Okay, so f of negative x equals negative x cubed minus 2 times parenthesis negative x squared. It's just a good idea, whether you're doing x or y, to do this in parentheses, just so that you do not forget or drop something. I'm going to also show you how this actually works out. Like technically this is negative 1 times x. Here this is negative 1 times x. So if I rewrite it like that, I technically have negative 1x cubed, which is negative 1 cubed, x cubed. Here, since I have negative 1x squared, I have negative 1 squared and x squared. Well, negative 1 cubed stays a negative, but negative 1 squared becomes a positive. Negative times negative is positive. Negative times negative is positive, times one more negative is negative. And so I end up with this equation, f of negative x equals negative x cubed minus 2x squared. Okay, and then you can see here that this indeed, the y-axis is sort of our mirror, that what we see on the left is exactly what we see on the right. Next, we're going to look at vertical stretching and shrinking, which uses an outside factor. Vertical stretching is making something taller. Vertical shrinking is making something shorter. And just as we had with vertical translations moving moving up or down, where we added or subtracted something outside, here we have an outside factor, which means we're multiplying the entire function by a constant or some value that's outside of the function. The graph of y equals the graph of y equals a times f of x can be obtained from the graph of y equals f of x by stretching vertically, and this is when we make it taller, when the value of a, the absolute value of a, is greater than 1. Okay, multiplying by 2 or 3 or 2.5 or 1.5. For example, if we wanted to stretch the function y equals x cubed minus x vertically, we could multiply the original function by any constant, and here we've multiplied it by 2. And you can see the original function in black, and the new function, the vertical stretched function, in green. So we've stretched this by a factor of 2. Okay, notice what they've done here. In order to stretch something vertically, we simply multiply the entire expression by that constant. If we want to shrink something vertically, or make it shorter, this happens when we have fractional values that are less than 1. 1 half, 1/4, 0.70, okay? So when a is a fraction between 0 and 1, the absolute value of a is between 0 and 1, this will make something shorter. For example, if we wanted to shrink that same function vertically, we would multiply the entire expression by a fraction, and here they've multiplied it by a factor of 1/10. So this function here that you're seeing in the graph is shrunk vertically by a factor of 10, okay? Because we're multiplying it by 1/10, all right? If the value of a is negative, not only does the graph shrink or stretch vertically, but it's also reflected across the x-axis. It's also reflected across the x-axis, okay? The y-coordinates of the graph of the stretched or shrunken vertically graph can be obtained by simply multiplying the y-coordinates of y equals f of x by that same factor. So if you if you graph this in your calculator, y equals x cubed minus x, and you looked at the table function, and you wanted to graph the other one, all you would have to do is multiply all the y values by whatever the value of a is. And of course, that would work in either case. So if you have the coordinates for your original function, you can find the new coordinates for the stretched or shrunk function simply by multiplying all the y values by the value of a, and that's what that last bullet is saying. So let's look at an example. Stretched by a factor of 2, the function y equals x cubed minus x, and reflected across the x-axis. So we have our original function here, In order to stretch by 2, we need to multiply the entire function by 2. But we're also going to reflect across the x-axis. So remember, we have to change the sign. We have to make the multiplier negative. Okay? So we're going to multiply both sides of this equation, or really the function, by a -2 to get our new stretched and reflected function. If we multiply that -2 out and distribute it, we get -2x cubed plus 2x. And here we can see that in the graph. Our original function is in black, and our reflected and stretched function is in, it looks like a little orange color or peach color. Okay? So we can see now that it's reflected across x, it's opposite and it's taller. Opposite and taller than our original function. It's opposite and taller than our original function. When we're talking about horizontal stretching or shrinking, this is an inside factor. And again, it was an inside factor, or working on the x value, when we were doing translations, moving left and right. F of x plus a constant. F of x plus a constant or minus a constant. So the graph of y equals f of cx, notice it's inside, it's a product inside, c times x, can be obtained from the graph of y equals f of x by shrinking horizontally. Okay, so this is when it's getting skinnier or thinner. And this happens when the value of c, the absolute value of c, is greater than 1. So shrink, for example, if we wanted to shrink y equals x cubed minus x horizontally, we could multiply we could multiply each of the x values by 2. So here we have y equals, or f of x equals x cubed minus 3. So what we want is f of 2x, f of 2 times x. And so we replace every x with 2x, the c value, the multiplier value, in parentheses before we do anything to it. Make sure you're using those parentheses for these horizontal shifts, right? Minus 2x in parentheses. Okay? We can also stretch horizontally, stretching horizontally, and this is where we'll make something fatter. And this is when we have fractional values. The absolute value is less than 1. So again, 1/2, 1/3, 0.8. These are fractional values less than 1. Okay? So again, if we wanted to stretch the same function horizontally, we would replace all of the x's. In this case, we replace them with 1/2 x inside parentheses, and then we would do the math. Okay? Then we would do the math. Notice if that multiplier is negative, if the c is negative, if it's less than 0, then this will also not only shrink or stretch, but it will also reflect across x. For x coordinates of the graph of y equals f of cx, these can be obtained by dividing the x coordinates of the original graph of f of x by that value of c. So again, if I plugged this into my calculator and I wanted to find the new x values, I would divide by that value of c. Okay? I would divide by that value of c. So here, if I'm dividing by 1/2, that means I'm multiplying by 2. Okay? So you're multiplying by the reciprocal, if that helps you in a different way, especially with fractions. Here I would be dividing each x by 2. Okay? It's important that you notice that this is the opposite of what we would expect. Fractions normally make things smaller, but here it makes it fatter, or fractions stretch while whole numbers shrink. And the way I remember this one, when I'm talking about fatter, which is a horizontal stretching, fatter is done by fractions, which both begin with the letter F. So let's look at an example here. This is our last slide for today, so we're almost done. We're going to stretch the function y equals x cubed minus x horizontally by a factor of 2 and we're going to reflect it across the y-axis. So remember, if we want to stretch horizontally by 2, we need to divide by that, divide the x terms by 2, which is the same as multiplying by 1/2. So wherever we have an x, we're going to replace with a 1/2 x in parentheses. In addition, since we want to reflect across y, we have to change that factor into a negative. So in order to get the original function stretched horizontally by 2 and reflected across the y-axis, we're going to have to replace each of the x's with negative 1/2 x. Okay? When we multiply this out, we get negative 1/8 x cubed plus 1/2 x. Okay? And that's just cubing negative 1/2, which gives us negative 1/8. And then, of course, negative 1/2 times a negative minus a minus becomes a plus. And we can see that graph here. The original graph is in black, and our new graph is in peach or orange. I'm sorry, I'm not always great with colors. Okay, again, these are like composite functions. It can be a little bit confusing. So this isn't a very long lecture, and I've got these slides pretty condensed. So if you need to, go back and reflect on these or watch again.